Determining the correct wire size for a standalone air conditioning unit involves several considerations, primarily focusing on the overcurrent protection device or OCPD requirements. The unit has a nameplate stating a minimum OCPD requirement of 25.4 amps and a maximum OCPD of 50 amps. The existing installation has a built-in 100 amp OCPD, which is problematic, and is fed from a 30 amp circuit using number 10 American wire gauge wire. The main fan motor has a full load amperage of 11.0 amps. Another two identical units use number 4 and number 6 American wire gauge wire respectively. Firstly, let's address the existing 100 amp OCPD built into the unit. According to the provided information, the unit tag specifies a maximum OCPD of 50 amps. Therefore, the 100 amp OCPD is too high and poses a risk of inadequate protection for the equipment in case of a fault. Secondly, the circuit feeding the unit is currently 30 amps, which is too low based on the minimum OCPD requirement of 25.4 amps for the unit itself. While it exceeds the bare minimum, it is still inadequate given the unit specifications and the presence of a main fan motor with an 11.0 amp full load amperage. Now let's consider the wire size. The existing number 10 American wire gauge wire is insufficient for a 30 amp circuit, let alone the potential 50 amp OCPD that the unit might require based on its maximum rating. Number 10 American wire gauge wire typically has an ampacity of 30 amps at 60 degrees Celsius, as per the National Electrical Code Table 310.15. The 16. However, it may be derated based on installation conditions such as ambient temperature or the number of current carrying conductors in a raceway. So what is the correct wire size? The correct wire size must be able to handle the load and be appropriately protected by the OCPD. Since the maximum OCPD specified for the unit is 50 amps, the wire must be rated for at least 50 amps after any applicable derating factors are applied. Number 6 American wire gauge wire is suitable for this application. Number 6 American wire gauge copper wire has an ampacity of 55 amps at 60 degrees Celsius, 65 amps at 75 degrees Celsius, and 75 amps at 90 degrees Celsius according to the National Electrical Code Table 310.15. Beat 16. The appropriate ampacity rating to use depends on the temperature rating of the terminals and the equipment and the ambient temperature conditions. Also, it's crucial to consider any derating factors that might apply. For instance, if there are more than 3 current carrying conductors in a raceway, the ampacity of the wire needs to be derated as per the National Electrical Code. Considering the 50 amp maximum OCPD requirement, the number 6 American wire gauge wire, with its ampacity ranging from 55 amps to 75 amps depending on the temperature rating, provides sufficient capacity for this application. In summary, the existing 100 amp built-in OCPD is too high and must be replaced with a 50 amp OCPD or lower. The 30 amp circuit is insufficient and should be upgraded to match the new OCPD rating. The number 10 American wire gauge wire is too small and needs to be replaced with number 6 American wire gauge wire. Always consult the National Electrical Code and local regulations for specific requirements and ensure that all work is performed by a qualified electrician. When selecting the appropriate overcurrent protection device and wire size for an air conditioning unit, several factors must be carefully considered to ensure safe and reliable operation. These factors include the unit's nameplate ratings, the National Electrical Code requirements, and the specific installation conditions. The unit nameplate provides crucial information, including the minimum circuit ampacity or MCA and the maximum overcurrent protection device or MOCP. The minimum circuit ampacity indicates the minimum allowable ampacity of the conductors supplying the unit, while the maximum overcurrent protection device specifies the maximum size of the circuit breaker or fuse protecting the circuit. The National Electrical Code provides guidelines for selecting the appropriate overcurrent protection device and wire size based on the unit's nameplate ratings. The overcurrent protection device should be sized to protect the conductors from overcurrent and short circuits while allowing the unit to operate normally without nuisance tripping. The wire size should be selected to carry the unit's load current without exceeding its ampacity rating, taking into account any applicable derating factors for ambient temperature or conductor bundling. Specific installation conditions, such as the ambient temperature and the number of conductors in a raceway, can affect the ampacity of the conductors. Higher ambient temperatures and conductor bundling can reduce the ampacity of the conductors, requiring the use of larger wire sizes to compensate. It is important to consult the National Electrical Code tables and rating factors to determine the appropriate wire size for the specific installation conditions. In addition to the unit's nameplate ratings and the National Electrical Code requirements, other factors may also influence the selection of the overcurrent protection device and wire size. These factors include the type of motor used in the unit, the starting current of the motor, and the voltage drop in the circuit. Different types of motors have different starting current characteristics, which could affect the size of the overcurrent protection device required. High starting currents may require the use of time delay fuses or circuit breakers to prevent nuisance tripping during motor startup. The voltage drop in the circuit should also be considered to ensure that the unit receives adequate voltage under load conditions. Excessive voltage drop can reduce the unit's performance and efficiency, and in extreme cases, can damage the unit. The wire size should be selected to minimize voltage drop and maintain adequate voltage at the unit's terminals. To determine the correct overcurrent protection device and wire size for an air conditioning unit, follow these steps. Firstly, review the unit's nameplate to determine the minimum circuit ampacity and maximum overcurrent protection device ratings. Secondly, consult the National Electrical Code to determine the appropriate overcurrent protection device and wire size based on the unit's nameplate ratings and the specific installation conditions. Thirdly, consider any other factors that may influence the selection of the overcurrent protection device and wire size, such as the type of motor used in the unit, the starting current of the motor, and the voltage drop in the circuit. Fourthly, select the overcurrent protection device and wire size that meet the requirements of the unit's nameplate ratings, the National Electrical Code, and the specific installation conditions. Finally, ensure that all electrical work is performed by a qualified electrician in accordance with all applicable codes and regulations. Here are some additional considerations for selecting the appropriate overcurrent protection device and wire size. Always use copper conductors for air conditioning unit circuits, as copper has a higher ampacity rating than aluminum for the same wire size. Use appropriately sized conduit or raceway to protect the conductors from physical damage and environmental factors. Properly terminate the conductors at the circuit breaker or fuse panel and at the unit's terminals, using appropriately sized connectors and torquing them to the manufacturer's specifications. Ground the unit properly to protect against electrical shock hazards. Inspect the wiring and connections periodically to ensure that they are in good condition and free from corrosion or damage. If you are unsure about any aspect of the electrical installation, consult a qualified electrician for assistance. Understanding overcurrent protection devices, or OCPDs, is crucial in electrical systems for safeguarding against overloads and short circuits. Overcurrent refers to any current exceeding the rated ampacity of a conductor or device. This excess current can generate heat, potentially damaging equipment, insulation, and even causing fires. An OCPD is designed to interrupt the flow of current when an overcurrent condition occurs, thereby protecting the electrical system. The primary types of OCPDs are fuses and circuit breakers. Fuses are one-time devices that contain a fusible link, which melts and opens the circuit when the current exceeds the fuse's rating. They are simple, reliable, and relatively inexpensive. Circuit breakers, on the other hand, are reusable devices that use a mechanical mechanism to trip and interrupt the circuit. They can be reset after tripping, making them more convenient than fuses in many applications. Fuses are categorized into different types based on their speed of response and current limiting capabilities. Some common types include standard fuses, time delay fuses, and current limiting fuses. Standard fuses are designed for general-purpose applications and provide fast protection against overcurrents. Time delay fuses, also known as dual-element fuses, can withstand temporary overloads such as motor starting currents without tripping. Current limiting fuses are designed to quickly interrupt high-fault currents, limiting the amount of energy released into the circuit. Circuit breakers are also available in various types. including thermal magnetic breakers, magnetic-only breakers, and electronic trip breakers. Thermal magnetic breakers use a combination of thermal and magnetic elements to trip on overloads and short circuits. Magnetic-only breakers respond quickly to short circuits but do not provide overload protection. Electronic trip breakers use electronic sensors and microprocessors to detect overcurrent and trip the breaker. Selecting the appropriate oct for a specific application requires careful consideration of several factors, including the circuit's voltage, current rating, interrupting rating, and the type of load being protected. The voltage rating of the oct must be equal to or greater than the circuit voltage. The current rating of the oct should be sized to protect the conductors and equipment in the circuit without causing nuisance tripping. The interrupting rating of the oct must be sufficient to safely interrupt the maximum available fault current at the installation location. The type of load being protected can also influence the selection of the oct. For example, motor circuits typically require time delay fuses or circuit breakers to accommodate the motor's starting current. Additionally, sensitive electronic equipment may require surge protection to prevent damage from voltage transients. When installing and maintaining octs, it is essential to follow the manufacturer's instructions and all applicable electrical codes. Octs should be installed in readily accessible locations and properly labeled to indicate their function. Regularly inspect octs for signs of damage or deterioration and replace them if necessary. Never attempt to bypass or disable an oct, as this can create a serious safety hazard. Understanding wire gauge sizes is fundamental to electrical work. The American wire gauge, or AUG, system is the standard used in North America for designating the size of round, solid, non-ferrous conductors. The gauge number is inversely proportional to the wire's diameter. A smaller gauge number indicates a larger wire diameter, and thus a greater current carrying capacity or ampacity. The AWG system is based on a logarithmic scale, where each decrease of 3 gauge numbers doubles the wire's cross-sectional area and approximately doubles its ampacity. For example, a number 10 American wire gauge wire is approximately twice the size of a number 13 American wire gauge wire. Conversely, an increase of 3 gauge numbers halves the wire's cross-sectional area and approximately halves its ampacity. The ampacity of a wire is the maximum amount of continuous current it can carry without exceeding its temperature rating. The National Electrical Code provides ampacity tables for various wire types and insulation ratings. The ampacity of a wire is affected by several factors, including its material, size, insulation type, and installation conditions. Copper wires have a higher ampacity than aluminum wires of the same gauge size. Different insulation types have different temperature ratings, which affect the wire's ampacity. Installation conditions such as ambient temperature and the number of conductors in a raceway can also affect the wire's ampacity. When selecting the appropriate wire gauge for a specific application, it is essential to consider the circuit's current requirements, the wire's ampacity, and any applicable directing factors. The wire gauge should be selected to carry the circuit's load current without exceeding its ampacity rating. Directing factors may need to be applied to the wire's ampacity to account for high ambient temperatures, conductor bundling, or other installation conditions that can reduce the wire's ability to dissipate heat. In addition to ampacity considerations, the wire gauge should also be selected to minimize voltage drop in the circuit. Voltage drop is the reduction in voltage that occurs as current flows through a conductor. Excessive voltage drop can reduce the performance and efficiency of electrical equipment. The wire gauge should be selected to limit voltage drop to an acceptable level, typically no more than 3% for branch circuits and 5% for feeders. To determine the appropriate wire gauge for a specific application, follow these steps. Firstly, determine the circuit's current requirements by adding up the loads that will be connected to the circuit. Secondly, consult the National Electrical Code ampacity tables to determine the ampacity of various wire gauges based on the wire's material, insulation type, and installation conditions. Thirdly, apply any applicable directing factors to the wire's ampacity to account for high ambient temperatures, conductor bundling, or other installation conditions. Fourthly, select the wire gauge that has an ampacity equal to or greater than the circuit's current requirements after applying any derating factors. Fifthly, calculate the voltage drop in the circuit using the selected wire gauge to ensure that it is within acceptable limits. Finally, if the voltage drop is excessive, increase the wire gauge until the voltage drop is within acceptable limits. In addition to these general guidelines, there are some specific considerations for selecting wire gauges for different types of circuits. For example, motor circuits typically require larger wire gauges to accommodate the motor's starting current. Lighting circuits may require smaller wire gauges due to their lower current requirements. Control circuits may require smaller wire gauges due to their lower voltage and current levels. Always consult the National Electrical Code and other applicable electrical codes for specific requirements and recommendations for wire gauge selection. And always ensure that all electrical work is performed by a qualified electrician in accordance with all applicable codes and regulations.